Okay, so at this point, you're probably wondering, like, why we're talking about center of mass right now. It seems kind of disconnected from momentum. It's like a concept that seems like it kind of came out of nowhere. Um, but the reason that we're talking about center of mass is because by looking at the center of mass of a system, we can infer a lot of information about how different objects in that system are moving. So at this point, you should have an idea of how to calculate center of mass, and you should have a notion of how the center of mass of a system behaves, right? So like if an object is thrown through the air, it's the center of mass of that system that will follow a parabolic trajectory, right? Um, but let's tie this more specifically into kind of what we're doing right now. So one sort of kind of important piece of information as a starting point for looking at a lot of different scenarios is that if the external force is 0 on a system, then the center of mass velocity of that system is constant. All right, and you should like write this down exactly as it is. So if the net force on a system is 0, or I guess if I wrote it, if the net force equals 0 on a system, the center of mass velocity of that system is constant. So let's go ahead and look at an example of this. So here, this is on this ophysics.com website, so you could find this if you want to play with it yourself. So I'm looking at this person on a raft, right? And this is really similar to the ball and the canoe video on, what was I going to say? On flipping physics. So here we've got a person. This person is standing on a raft. So if we assume there's no friction underneath the raft, and we let this person walk across the raft, right? Notice the person's center of mass is moving to the right. The raft center of mass is moving to the left. But the center of mass of the system is not moving. And that's because, right, the center of mass of the system started with 0 velocity, so it maintains 0 velocity with no external force. Right, so if we come back to this, right, the net force on that person raft system is 0, and any forces in between the two is an internal force. So the velocity of the center of mass of that system will remain at 0. Right, and it doesn't matter how heavy you make the person or how small you make the raft. Right, so if we make the person heavy, notice the center of mass gets closer to the person. Same thing if we make the raft lighter, right, the center of mass of the system is closer to the person. And if we let the person move, the center of mass of the system should still stay in the same place, right, because it has 0 velocity, and if there's no external force, then that system will, the center of mass of the system will keep a 0 velocity. See that? Okay, now let's go ahead and look at this in the context of a collision. So this is the same collision simulation that we played around with before, but I am going to make it so that we can see the center of mass of the system. So why don't we look at an example where the two masses, let's say, have, or the two blocks have the same mass. And let's maybe put the blue one at rest and start the red one out with some speed. And notice that the center of mass is right in between them, and that's because they have the same mass. And I want you to watch the center of mass as this collision occurs. Maybe we can make it inelastic. Okay, so let's go ahead and run it. Oh, wait. I wanted to make the blue box 0 initial velocity, not -10. Let's keep it simple. All right, let's give this a shot. And then when they collide, right, the center of mass velocity doesn't change, because when the two blocks collide, they exert forces on each other, but there's no external force. And over here, let's run it one more time. Right, if we look at the graphs on the right where it says P, right, notice that the black graph, that's the momentum of the system, is constant. And also notice the top graph where it says V, right, the center of mass graph, the black one, that remains constant. So let's go ahead and look again. So if we look at those velocity graphs, oh, come on. I can't really zoom in. If we look at the velocity graph, right, at the top right, the center of mass is the black velocity in between them. And when they collide, the center of mass velocity stays constant, right? And it doesn't really matter how we set this up, right? So let's say we give the two blocks velocity in opposite directions. Oh, come on. Gotta type it. There we go. Oh, seriously? Frustrating. There we go. Okay, so what this means now is they're moving in opposite directions at the same speed. They have the same mass. So the center of mass actually shouldn't move. And when they collide, the center of mass keeps that zero velocity. Boom. Right, and we can see that in the graphs too. So if we look at the top right, the center of mass velocity was 0, and that's because the two objects had, equal mass, and they were moving towards each other at the same speed. So the center of mass started with no velocity, it also ends with no velocity. Right, and we could change this system in any way, right? We could make the collision elastic. We could, let's say, slow down the blue box a little bit, speed up the red box, and when they collide, if we follow that center of mass point between the two objects, right, maybe I'll make this one lighter weight. If we follow the behavior of that center of mass, it should keep a constant velocity throughout the entire interaction. You see that? When we look at the graphs, that center of mass velocity kept a constant speed, right? Let's look at it again. Right, so because the interaction of the boxes is an internal force, the center of mass of the system does not change its velocity during that interaction. Okay. So, what does this mean if there is outside force on the system? Well, if there is outside force on the system, so if net force is not equal to 0, V center of mass changes, and these should technically be vectors. V center of mass changes in direction of, and I guess we should be really particular. We should say V net force on a system V center of mass of that system changes in direction of net force. Right? In other words, we could actually use the impulse momentum equation on the whole system. So I could say the net force on a system times the time over which it's applied is actually equal to the change in momentum of the system. And that's actually equal to the mass of the system times the center of mass velocity. I guess the change of that. Change in mass of the system times the center of mass velocity of the system. So this is basically the impulse equation, but we can apply it for an entire system. So let's go ahead and look at an example of this. And I think really the easiest way to illustrate this is through examples. Okay, so let's say we've got two boxes. Maybe I'll use this fancy drawing tool. Let's say we've got two boxes of different mass. And maybe they're squished together. So they're pretty close. And let's say there is a spring in between them. And beneath them is the ground. Let's say it's frictionless everywhere except here. So here's friction, and this part is frictionless. And let's say that that spring shoots those masses apart from each other. So the center of mass of the system is going to be right closer to the big object than the small object. So it's probably right about there, assuming those masses they're made of about the same material. And those objects, when they shoot apart from each other, the big one's going to move to the left, the small one is going to move to the right. The center of mass of the system actually shouldn't move, right? Because that spring force between them is an internal force. So, when they shoot apart, right, so that spring is going to have extended, and let's say the spring is not actually connected. So this one will move this way, this one will move that way, this one will be moving fast, this one will be moving slower. V center of mass will still equal 0, right? V center of mass was 0 here, so it stays equal to 0. Yeah, and this is because there hasn't been any external force on the system. And that spring, right, that spring will just be extended and just kind of hanging out in between them because it wasn't actually connected to either. And they're cruising along, but notice that there is some friction. So at a later time, right, if we keep sort of following with what's going on, this will have moved along this way, but this at some point will hit that friction patch, right? And when this hits that friction patch, there is a force to the left. And that means that in this two-object system, there is now a net force to the left, which means that the system had 0 center of mass to begin with, but the system is receiving an impulse to the left. So that means the system is going to gain velocity to the left. So the center of mass is actually going to start to move. And now the VCOM is going to be to the left. And this makes sense, right? Because eventually, if this is in friction, this is going to come to rest at some point. And if this comes to rest, and this is still moving to the left, well, the center of mass point between those two objects is going to keep moving to the left, right? Because it's going to keep the same distance sort of in between those two objects. So, right, if this stops, but this is still moving, the center of mass point is going to keep moving to the left. And the reason for that is because friction exerted a force on this block, on the system, to the left. And that's why the center of mass of the system didn't keep a constant velocity, right? The center of mass of the system gained velocity to the left in the direction of that net force. So I hope this was helpful in giving you an idea for how center of mass is actually useful and how we can use it to understand things like collisions. Basically, just keep coming back to this, right? If the net force on a system, right, so if the outside force, the net outside force on a system is 0, the center of mass of that system will keep a constant velocity, right? VCOM is constant if the net force on the system is 0. And, right, internal forces are not, like, they're excluded from this, right? So this is only external forces. And if the net force is not 0 on a system, VCOM of that system will change in the direction of that net external force. All right, I hope this was helpful.